All right, so welcome to class. If you are someone from the 11 o'clock class, I apologize for missing out on class time with y'all. I'll be completely honest. So I live in Tech Terrace, the neighborhood to the south of campus, and I walk in when the weather is nice, such as it is today, and I got all the way here to the building and realized I'd completely forgotten my keys. So I had to walk back home and get my keys. So that's why we didn't have class at 11. But we're going to do this and cover all the same stuff. And we'll record it and put it on YouTube. So hopefully everything's fine. And of course, I got office hours today and on Wednesday. Ari is available right now. So if you want to skip out in class and just go talk to her, that's a thing too. So does anyone have any questions, comments, concerns about anything going on right now? Don't forget you got that first project to do tonight. The second project is available. Also, assignments 11 and 12 are also available right now. I noticed yesterday when I went to post assignment 12 that I actually had never posted assignment 11. So that's up there as well. And that'll be due in a week. And assignment 12 is due a week from this Friday. So that is that. And really, we only have like 2 weeks of class left. So anything? Any questions, comments, concerns? We are very much on the home stretch, man. It is almost in the books. All right. In that case, let's get into today's topic. I've recently fallen in love with the random video slide background that the machine learning design tool in PowerPoint generates from reading the title. So I have no idea how a waterfall is relevant to registers and register transfers, but the AI seem to think so. It's like a waterfall of knowledge that is coming down upon you. I really can't think of a good metaphor between registers, but there must be something. There was something in the machine learning algorithm that PowerPoint uses that thought that this was the appropriate video background for this title slide. The water is transferring from the top. Yeah, really that's what it is. Adrian's got it. It's just like, dang, this must be an important topic. We put extra production value on top of it. It just only has waterfall videos. Yeah, that's really all it is. There's no algorithm. It's just waterfall videos. All right, registers and register transfers. Let's dig into it. This is section 12, 12.2, I believe, from the course textbook. We're going to talk about registers. We're going to talk about data transfer between registers. We're going to talk about, and then we're going to finally talk about this parallel adder with accumulator, which is kind of a good example of what we talk about, or what we mean when we talk about registers and register transfer operations. And then finally, we'll kind of break out of PowerPoint. We'll open up VS Code, and we'll do some sequential circuit stuff in Verilog. And I think you'll find the sequential circuit stuff in Verilog is a lot more similar to the kind of programming that you're probably used to if you've programmed in C or Python or something like that. It's gonna feel pretty normal. So let's go ahead and dig into it. First, let's talk about registers. A register consists of a group of flip-flops with a common clock input, right? So we've already talked about just regular flip-flops that have, a clock, a D input, and a Q output. And if you imagine that one flip-flop is just one bit, if you want to store multiple bits of information, you got to have multiple flip-flops. A register is just a group of flip-flops. So if you only have one bit, all you need is a single flip-flop. But a collection, it's like a flock of geese, a herd of buffalo, a pack of wolves, and a register, a murder of crows. Yeah, that's another one. And it's a register of flip-flops. So a register is just a group of flip-flops. So when we start talking about it, really just remember It's just a bunch of flip-flops. They're all going to do the same thing. So, and registers, well, we just talked about it, are commonly used to store and to shift binary data. We'll talk next time on Wednesday about what we mean by shifting binary data. But today we're just interested in storing binary data. So let's take a look at a pretty basic register and just kind of unpack here. So first off, we have some D flip-flops, but there's some other things going on here. So let's kind of unpack it. My first question is, all 4 of these flip-flops, let's say 1, 2, 3, and 4, right? All 4 of these flip-flops are all edge triggered D flip-flops, but are they rising edge or are they falling edge flip-flops? Class. Yep, the dot equals falling. So if we look and we see a little dot there on the input to the clock signal, that means it's a falling edge. So falling or negative edge. Ooh. Can't do it. Okay. So that's a negative edge. The other thing here is we didn't really talk about this last time, but this clear signal on the flip-flops. Now, it's got a dot 2, which means that it's going to operate, it's called, it's going to operate at a 0. So what this means here is that this signal, CLRN, clear in, if CLRN is equal to 1, then be normal, right? Normal operation. When you see the clock, upload the stuff. But when CLRN is equal to 0, then we're going to reset, which is to say that Q equals 0. So we can use this clear signal to erase the value in the register, right? So we're loading value from these inputs. And then if we just set clear to 0, then they all click over and they all go to 0. So that's just a way to quickly wipe the information on the register. So it says whenever the rising edge or the falling edge happens, is in this case, if clear is equal to 0, that then you ignore D and you just say Q is equal to 0. So that's clear in. Any questions about that clear signal? That's the only real weird thing that's going on here. The other thing is this load signal is basically just gives us a way to control if we're going to put data into it or not, right? We don't really know what mechanisms are in place to create this data, but sometimes we want to make sure that we're not loading data until all the data is ready to be loaded. So by simply tying this load signal to the clock signal through an AND gate, that just means, let me write it up here, right? So if load equals 0, then if we say that's our clock signal, yeah, if load equals 0, then our clock is 0. But if load is equal to 1, right? Because remember, 0 and x is equal to 0, and 1 and x is equal to x. So if load is equal to 1, then the clock is just equal to the clock, right? So that's all that's happening there, right? When load is 0, the AND gate drives everything to 0. When load is 1, then the clock is just going to pass through like normal because it's an AND gate. And so when that happens, because there's dots on the clock signals, on the falling edges of all these guys, whatever the data is on these input lines will load into the outputs. Cody asks, so then the register doesn't start operation until load equals 1? You're absolutely correct. Yeah. So only when load is equal to 1 will the register operate. Otherwise, the register is sort of off and it's not updating. Now, it's still going to be having these outputs, right? Whatever value was put on the outputs is going to stay there while load is 0, but the register isn't going to update at all while the load is equal to 0. It has to be equal to 1 for it to get new data. Cool. Any other questions about this one? Well, that's really all there is to it as far as registers go. Let me see, Liam's typing before we go to the next slide. What do you use them in? Memory, right? Straight up, right? In a hard drive, in RAM, registers are where we store bits. So if we say, and very often we use 8-bit registers to do stuff, which is why, well, registers are the size of the memory space for the thing. Hold on, let me back up. That was a terrible explanation. Registers are memory devices. So if you want to store bits of information, you use registers. The size of a processor, so if you've heard of a 32-bit or a 64-bit processor, that is directly referencing the size of the registers in the processor. A 64-bit processor has 64-bit registers, which is to say registers that consist of 64 flip-flops to do all the information. A lot of times in RAM, there will be, 8-bit registers that are sitting there to collect the information, stuff like that. Registers are memory. Memory are registers. And an SSD drive, it's just registers. Just a big library of registers that you can access. Cody asks again, do all the bits click over at the same time? Yes, that is the purpose of the clock. Because you want to keep them in sync with each other, you want all of the flip-flops in the same register to change at the same time. That is why we use the clock signal. So all 4 of these flip-flops will update with new information on the falling edge of the clock. So it makes sure that they're all changing at the same time. Now, of course, if you're working on like a modern, 64-bit processor, you might have that's, clocking at 4 gigahertz or something like that. You might have some weird stuff, some weird timing issues, such as, the falling edge will arrive here faster than it arrives there, right? Because the wave has to propagate down the transmission line. But that's way outside the scope of this class. For this purposes of this class, they all happen at the exact same time. All right, let's go to the next slide, which is basically the same one. So this is the same register as the previous one. We just made one sort of clear distinction. We've taken that load signal, and instead of having it tied to that AND gate, we've just brought it inside the flip-flops and called it clock enable. So we say CE is equal to clock enable. So that's going to behave exactly the same as before, which is to say that if, CE equals 1, then, be normal. And if CE equals 0, no update. And that's why this load signal is tied to that. Now we could, if we wanted to, right, we could make it so that you update on load equals 0, right? If we put a dot on the input, then that might say that, we're going to load on the 0 signal. But other than that, everything here is exactly the same. Just a little bit of a shorthand, so we don't have that big AND gate sticking out there, and everything is nice and clean. Next up, and finally, when we write a register, we typically don't draw out all the flip-flops. We draw one and then use bus notation, right? So this is all of the components of the flip-flop, right? We've got the clear that's on the 0. We've got the clear enable that's attached to load. We've got the clock that's got the negative edge. And we've got D and Q. But all we've done here is just say the number of bits. We've used bus notation. To represent the registers. So if you see a symbol that looks just like this and has, just 1 bit coming off of it, that's a flip-flop. But if you see bus notation, that's just going to be a register of flip-flops. In this case, it's a 4-bit register. Any questions about this diagram? Or the sort of general concept of registers in general? General concept in general. Registers just a bunch of flip-flops. Okay, let's keep it moving. So now let's talk about data transfer between registers, right? Because typically what we're doing is we're pushing data around to different registers to do different operations. When you store a value in a variable, right? So if you are writing, in C, and you say something like int x equals 5, what you're saying here is, store 5 in register at location X, right? So the system will actually assign an address to X and say, well, let's put a 5 at that address. And if we say, int y equals a plus b, right? This is going to say add the values in register A and register B, store the sum in register Y. All right, when you use variables in your code, what you're really doing are using registers inside your processor or inside RAM. So that's the gist, right? We're always pushing data around to different registers and doing operations on them. We take them out of registers, we do math, we put the results back in registers. Yep. Kaylee asks, so in Verilog, does reg correlate to registers? Exactly. That's just, reg says, make a register that does, that stores stuff, which is why Verilog doesn't make the distinction between, there's no ints or floats or strings or like that in Verilog, it's just registers. And it's the same thing in C++, yeah. In all languages, this is how it works. When you get to, you probably won't do it in your intro to programming classes, but in your data structures class or your more advanced programming classes, you'll talk about pointers, which is where you can use your code to grab the address of the value. An array is a register that stores the addresses of other things. It's a whole thing. Waiting for these guys to finish typing here. Yeah, pointers in C. Once you can wrap your brain around what a pointer is in a programming language, yeah, it also leads to memory leaks. But yeah, once you can wrap your brain around what a pointer is in C or another programming language, it's like a whole superpower that you've unlocked in your programming. So, but let's talk about data transfers. So here's a really simple setup for transfer between two registers. So here we have a total of 3 2-bit registers, right? We have register A, that's 2 bits. And notice they've really simplified the flip-flop notation, right? There's no weird stuff, there's no clear, there's no load. They don't even draw the clock signal, but we assume it's there, right? There's register B, and then we have a register Q. Now, there is this enable signal. So there's some values in register A and register B that in this diagram we don't really care what they are, right? There could be anything. It could be 0, 1 or 1, 1 or whatever inside that register. Now, notice that we have a tri-state bus that connects all of the outputs to these new sets of registers, right? And the first bit, the A1 and the B1 in both cases, tie to the D1 of the Q register's first flip-flop, and the same thing for 2. And then the only thing that's going on here is that there's a load enable, there's a clock. We already know what that does. And this enable here, I think calling it enable is kind of a mistake that the book makes, right? This is not really enable. Another thing you could think of is that this is an address, right? Because we're saying, well, where do we want to get our data from? Because if we write a 0 on this enable signal, well, that means that we're putting zeros So let's say 0 on enable means zeros on all of the tri-state buses, which means Z's here. But that means that we're drawing a 1 on the enables going to B. So we have a 1 and a 1, which means that the values going into D1 and D2 are B1 and B2 respectively. So let's write that out. Let's say that enable, if enable equals 0, then Q equals B. And on the flip side, if enable equals 1, then Q is going to be equal to A. And all of that is going to happen on the clock. The take-home message from this is we've got tri-state buses on the outputs of your registers. And really, a lot of the time, you'll see this sort of built into the flip-flops themselves. And we use the tri-states on the outputs to control when a register is reading and writing. These are going to kind of act like multiplexers between each of these two guys. So any questions about the concept that's going on here? We're just passing data from A to Q or B to Q, and we're using that enable signal to select which one we want to pass, right? And the mechanics of that happen through the use of this tri-state structure that we have on the outputs of all of our A and B register flip-flops. Any questions about that? All right. So let's take a look at this. This is basically the same structure. It's just going to be a little bit different. We've got the tri-states here. 1, 2, right? And each one is attached to the output of this inverter, which basically means that if enable equals 1, nothing happens. But if enable equals 0, then the output is passed to another register. So basically exactly the same thing we saw before, just on one register here. So let's blow this up. Here's a really messy example. Not really a messy example, but here's an 8-bit. And we know it's 8 bits because all of the bus lines here are all 8 bits. So this is an 8-bit register system. And let's see, there's a lot going on here. There is, well, we've got these 8-bit buses. We've got register A, and register B, and register C, and register D, all in the same line. And then here we have LDG and LDH attached to clock enable. And then we've got a decoder down here on the bottom where we've got E and F, and the outputs of the decoders. Notice that we've got this weird bit where we're inverting and then inverting again. But the outputs of the decoders are driving the enable signals, such as these, for each of the individual registers. So my question for you guys as we unpack this, if I say that E and F are equal to 0, 0, and LDG is equal to 0, and LDH is equal to 1, what happens? Oh, good catch. There's nothing up here, I just wrote 8-bit. So there we go. I've written our little question up here. If EF, which are the inputs to this decoder, are equal to 0, 0, LDG is equal to 0, and LDH is equal to 1, what happens? Yep, you're absolutely right, Joshua. A gets passed to H. So let's game that out, right? So if we have 0, 0, yep, Cody's right too. H equals A. So if we have 0, 0 on E and F, notice the inverted outputs here. That means we're going to have 0, 1, 1, 1 on the outputs of the decoder, which means that we'll have 0, 1, 1, 1, which means that only, because of the dot, means this happens on the zeros, it means that only register A is going to be active, which means signal will only be coming out of register A, not the other ones. And if LDG is set to 0, that means clock enable for register G is equal to 0. So register G can't be updated, but LDH is equal to 1, which means that register H can be updated. So that means that the value of A is going to be output, and it's going to be accepted by register H. So yeah, so that means that reg H will equal A and not be updated. Isman asks, how do I know that that's 0, 0, 1? Well, for two reasons. One, because I know how a decoder works, and my input here is 0, but also the inverters, right? A normal decoder would be 0, 0 gets us 1, 0, 0, right? And then 0, 1 gets us 0, 1, 0, 0. And 1, 0 gets us 0, 0, 1, 0. And 1, 1 finally gets us 0, 0, 0, 1. But because everything is inverted, it all flips over, and that's how we get 0, 0, 0, 1. Let me do one more. I'll write it down here on the bottom. What if I said that let's say EF is equal to 1, 0. LDG is equal to 1. And LDH is equal to 0. While you're thinking about that, Liam asks, why do you want to pass information from one register to another? Because you got to put information places, right? So when your code is executing, right, you need to. So for example, we got to pass information from your RAM into your hard drive, right? Registers are where we store information. We have to. When we're crunching numbers, when we're doing the math, when the processor is running and sort of chugging out the calculations, you got to have a place to put the numbers, and you also got to have a place to get numbers from. So it's not very common that we pass information directly from registers into other registers. Oftentimes what happens is we take information from registers, and they go through some kind of combinational logic, like an adder or a subtractor or a logic element, and then gets output to a register. But the short answer to why do we want to pass information from one register to another register is because it's useful to be able to move information around, right? We've got some information stored in one place, and we want to maybe move it around. So many algorithms depend on just being able to push information around in places. Take numbers out of the hard drive, put them in the processor, take them out of the processor, put them in RAM, take them out of RAM, do some crunching on them, then put them back in a different place in RAM, stuff like that. Cody, Aaron, and Sungjoon say C equals C, or C equals G, or G equals C. Yeah, so let's unpack. So a 1, 0 on EF is going to give us what? 0, 0, 1, 0, which means 1, 1, 0, 1, which means only register C will be active. And since LDG is 1 and LDH is 0, it means register G is taking in information. So yeah, that means that register G will get the value that's held in C. Any other questions about that? It is a beautiful thing, Cody. Somebody tell Liam. Liam's a non-believer. We just want to move data, man. We just want to take it and put it places. All right. What happens when LDG equals LDH? Well, so that is a little bit nonsensical, right? Because that depends on what they are, right? So, for example, if LDG is equal to LDH and they're both equal 0, right, then neither register will update. But if LDG equals LDH and they both equal 1, then yeah, both would update, right? Then we'd see that, if we were doing the same thing as down here, right, we would say that both G equals C and H equals C, right? We can update both registers, and there might be plenty of reasons why we would want to do that. So yeah, they're independent of each other. We can write to none of them, or we can write to one of them at a time, or we can write to both of them. It just kind of depends on what the application is and what the algorithm is that we're trying to implement. Good question, though. All right. So with that, let's go ahead and talk about a parallel adder with an accumulator. So in computer circuits, it's frequently desirable to store one number in a register and add a second number to it. That register that we stored in is called an accumulator. For example, if I pull up, has anyone ever, or hold up to the camera, anyone ever wondered what the AC button on your calculator stands for? Anyone want to guess now what it stands for? It does not stand for all clear. It stands for accumulator clear. Yep. So we clear the accumulator. So if I do something like, let me get like weirdly up to the camera. Here we go. 2 plus 3 equals 5. Now 5 is stored in the accumulator. And if I do plus 6, I get 11. Now 11 is stored in the accumulator, right? And I didn't have to put, if I do plus 8, right, I get 19 in the accumulator. I don't have to retype 11 plus 8 to get 19 because 11 is already stored in the accumulator. And that's just simply a register that does that. And that register is called an accumulator. So let's see what that looks like. So we've got an accumulator and we've got an adder. And there's some stuff going on here. And this diagram kind of makes it so that it could be any number of bits that you wanted. But the concept here is pretty simple, right? We have a full adder, right? Such as the kind that we've seen in class already, like the kind that you should be building right now for your first project, right? It's just an adder. It takes in, you got carry in, it's got carry out, that goes to carry in, right? It's a ripple carry adder. But here's the interesting stuff. So there is a clock and a clear in signal. And there's also what they wrote as AD, which is kind of dumb in my opinion. It should have been ADD because it stands for add. And notice that add is tied to the clock enables, which means that we only want to do the math when we want to do the math. Does that make sense? And now our output Q, right, could also be, not that last one. Erase. All right, these could all be outputs. But notice that the value is brought back as feedback into each of the adders, right? It comes back around as feedback into each of these adders, right? And we have an output S, that's the sum, and S is equal to X plus Y. All right, so what that means is, and then there's the carry that does the carry stuff. The clock runs, we can clear out the registers or write zeros to it, or we can keep adding it. So if we write, any number to this, right, 0, 1, 0, 0, let's suppose that there's all zeros in here. Now if there's all zeros in here, then I'm going to have 0 plus whatever the bit is, right? So I'm going to have 0 plus 0 gets me a 0, right? These numbers are just going to load into 0 into the registers, or into the flip-flops of the registers, and then they'll pass back around. So if I were to then turn around maybe scratch these out and say I want to do +6, 1, 0, or excuse me, 0, 1, 1, 0. Now I've got 0 plus 0 is, well, still 0. Then 0 plus 1 is, or excuse me, now it's, what was it? 1 plus 1 is going to be 0, 1. So I'm going to write a 0 here and carry a 1. And then have what? 0 plus 1 is still going to be a 0, carry the 1. I might be screwing this math up. Put a 1 there and a 1 on the output, which makes sense. That's 8. 1, 0, 0, 0. So that was a little bit confusing and not a great explanation on my part. It got a little messy, but the gist is S is equal to X plus Y. Every time you add, that value S gets put back in X, right? It gets stored in X. So you can kind of constantly be running out. And then when you press AC on your calculator for accumulator clear, what you're effectively doing is saying, well, I want to make clear in equal to 0. And then it wipes everything out and just puts a 0 back in the accumulator. Yes, this is where your calculator memory comes from. Liam asks, how many logic components do you think are in those super simple solar calculators? Those really cheap ones are usually, they're usually 8-bit registers, and they usually do just addition, subtraction, and multiplication and division. But more than likely, they just do addition and subtraction, and then there's a little bit of code written into the, like a really simple code, or maybe even just like some circuits that implements a multiplication algorithm by, you know, adding a certain number of times and then divides by subtracting a certain number of times. There's probably not, even in modern processors, there aren't usually dividing circuits. Division and multiplication are usually done with algorithms, and you're really just doing addition and subtraction. Okay, but it can run Doom though. You bet it can, man. There's a great meme that I saw a couple years ago that was like, what's the difference between a computer scientist and a computer engineer? And it was like, they both find like a piece of like alien technology, like an alien computer. And then, you know, the computer scientist is like, oh my God, what can we, you know, how can we use this to unlock, you know, the universe's secrets? And then the computer engineer is like, yeah, I got Doom to run on this. And that's the difference between computer scientists and computer engineers. And electrical engineers are supposed to take it apart for money. All right. So let's see. Before we move on, are there any questions about the parallel adder with accumulator? You basically just add and you're storing one of the values. Okay, one last thing, so we're actually running out of time almost, is notice that if we wanted to get zeros into the accumulator, we could hit the clear and write all zeros. But what if we wanted to put a number into the accumulator first before we did any addition? There's two ways to do it. The first one is to do just one step of addition. Do 0 plus a number gets you the number that's in Y, pushes it into the accumulator. But if you want to, but that takes 2 steps. If you want to do it in 1 step, you can change things up a little bit. So here's just 1 bit of what we just saw. But here they've added AD and LD, right, for add and load. And notice the load signal, so in both cases, both are tied through an OR gate to clock enable, so that if add is 1 or load is 1, it doesn't matter which one is which, the clock will still run. But notice that load enable now is tied as the selector for this multiplexer. And what happens here is it says that if load is equal to 1, then we grab Y directly and pass it through. But if load is equal to 0, then we do the addition. So it's, you know, if load equals 1, then D is equal to Y, and if load is equal to 0, then D is equal to X plus Y. So just a little bit of an optimization, right? It's more hardware, right? It's more circuitry, but it's going to save us more time. It's going to make our processor a little bit faster because we can load in one step instead of needing 2 or more steps to load up that information. Any questions about that? Okay, let's. I was talking about 7 minutes, so I wanted to talk about some sequential circuit stuff in Verilog. Let's do that. We're gonna go real fast. Discard. Let's pop open Visual Studio Code. Let's take a look at some. Whoa! What have I done? I gotta go back and. Everyone's going to go back to YouTube now and like freeze that frame and get the solution to the first project. I'm going to have to go back and edit those half a second out of the video. Okay, let's do this. Let's say that I want to do some sequential logic. I'll just call it sequential.v module test. Let's do some stuff. Let's say we got A, we got B, we got a clock, and we got Y. All right, we're just making some stuff up. End module, ooh, and let's go ahead and add, let's do a clear in as well. Stop. All right, there we go. So the same thing, we're gonna have inputs. So data inputs. Control inputs, but now we're gonna have registers. So we'll have A, so input A, input B as our data inputs. Let's put control inputs. It's still an input, right? Input clock and input clear in. And then for our registers, so now what we want to do is we'll have reg. Ooh, actually we got to do this too. Let's make them more than 1 bit. So let's say, let's go 8 bits. So we'll say 7 to 0, 7 to 0. So these are going to be 8-bit registers. Control inputs are just 1 bits, and we're going to have an output Y, which is also 8 bits. So let's say, let me do some comments here. Let's say that we want to do, you know, if, let's go on the rising edge. We'll just say Y is equal to, so if clear in is equal to 1, then we'll say Y is equal to 0. We'll clear everything out. And then if it's not, then we'll say that Y is equal to A plus B. So really simple, right? So the way we do that, we kind of saw that in our combinational logic discussion before, but we're going to say always at, open and close parentheses, and then since we want to go on the rising edge, we're going to say on the pause edge of the clock. All right, if I wanted to go on the falling edge, I would say the neg edge of the clock, but I want to go on the pause edge. Begin and end, and then really simply all I want to do is just say if clear in, well, equals 1, so I just got to leave it like that. Begin and end. We'll say Y. Here's where I think it's weird. I'm going to use this symbol. Less than or equal to 0. This is what's called a blocking assignment. If you want to make sure that your stuff happens kind of in sequential order, right? If you want your stuff to sort of work from top to bottom, then you use what's called a blocking assignment. And basically says that nothing will happen until this is finished. Whereas if you used a regular non-blocking assignment, then other weird stuff that can happen. But the basic gist is, if you need like a rule of thumb and don't really care about why you're doing it, is if you're doing it inside of these always at blocks, use this syntax. But if you're doing the normal sort of combinational assign business, use a regular non-blocking assignment. So we can do that later. So if clear is equal to 1. So notice I didn't put equals 1 or anything like that. If it's just 1 bit, then it's going to execute like normal. This is exactly the same as, you know, equals 1. And I'm going to say else, begin and end. We'll just say y is blocking assignment is equal to a plus b. And there we go. All right, so we are pretty much out of time, and that's all there is to sequential logic. It's not hard to see that this is a little bit easier. If you've got some programming experience, it's going to feel a lot more normal to you than the combinational logic that we've been doing. We will pick up with this on Wednesday. I'll show you how to write the test bench. I'll show you how to simulate a clock in a test bench. We'll do that first thing on Wednesday before we dig into the other lecture material. One last thing I want to go over though is from current slide. Is your next project that it is available now. It is due a week from today. It's due in a week. And what I want you to do is I want you to implement in Verilog the 8-bit parallel adder circuit with load selection that we saw. They're in 12-5 and 12-figures 12.5 and 12.6 of the course textbook. But what we're talking about are these two guys. I want you to make this circuit. I want you to make it 8 bits, implement all of this stuff, but also include this action right here where you have the load and the add signals. So there's a more detailed description on Blackboard, and we could talk about it in more detail on Wednesday. But are there any questions right off the bat about what you're supposed to do? Basically just implement the circuits that are in these two diagrams. So use this 8 times. Liam asks, so I take it that greater than or equal to doesn't work in Verilog? It not like that, it doesn't. It has its own weird syntax. It is if you wanted to do that, you would say something like less than equal. You still use the double equal sign. Yes, they are both due. Liam's asking, project 2 is due at the same time as assignment 11. Yeah, I believe that is the case. Let's double check. Let's go to the schedule. Let's see what we got here. We are on Monday. What day is it? The 9th. Yes, here we are. So assignment for unit 12 is due on the 20th. Project 2 is due on the 16th, which is, yes, the same day as assignment 11. And next time we'll talk about shift registers. So I'll hang out for another few minutes, but that is all I've got for you guys today. And so if there aren't any other questions, or if you don't have anything else you want to talk about, I'll see you guys on Wednesday. And I'll be here in the lab working during my office hours. So, and I'll have the speaker on. So if you come to my office hours, just like hop on and shout. I'll be here in this room and I'll hear you and I'll come talk to you. All right. See you guys later. Thank you.